Science 10s. This is Chemistry B Lesson 7, the mole and molar mass. So this one, it'll feel like we're switching gears a little bit, but you'll see how all the skills that we have from the previous lessons will continue to apply. So it's going to feel a little different because this word you've seen before as a little weird rodent that lives underground and digs holes and stuff. But we're talking a little bit different about moles here. So it says, remember that words are often used to represent a common number. So if I say, can you go grab a dozen eggs? You know to grab 12 eggs. If I say, grab a dozen pencil crayons, you would know to grab 12 pencil crayons. If I say, um, get in a group of a dozen, you would know that 12 would be that. Or if I say, grab a pair of socks, you know that's two. Grab a pair of earrings, you know that's two. I don't know what some of these I don't necessarily know. I think this is related to paper, so a ream of paper is 500 sheets of paper. These two I don't actually know. A score? Gross? I don't know what that means. So those ones are a little bit funky. But sometimes we use words to represent a number. So something like century is 100 years. I don't know why we would use century as a different way to express 100, but sometimes words can express numbers. So in chemistry, we have a unit that is called the mole. The symbol that we use for it is MOL. I don't know why. I guess dropping one letter is one less letter to write, but doesn't seem like that much of a time saver. So we'll see our units typically as MOL. If you write mole with an E, I'm not going to freak out on you or anything, but just know that if you see that, we didn't spell it wrong. That's just kind of the units that we'll use or the symbol that we'll use for it. In the same ways that you can have a dozen eggs or atoms or cars or apples, you can also have a mole of eggs or atoms or cars or apples. So though it would take you a very long time to eat 1 mole of apples, a mole is just another name for a specific number. So this one is so hard to visualize, and this is one where I like being at school because I can show you what 1 mole of water actually is. I can show you what 1 mole of table salt actually is. It's representing the same number of molecules of something. So what a mole actually is in terms of a number is not nice little numbers like dozen or pair or ream. It's actually a huge number. So 602,200 and then just tons of zero. In words, it's 602 hexillion, 200 pentillion. Never going to ask you to write that again, but just know that it's a ginormous number. So we generally use, we'll put it in scientific notation instead. So if you think back to physics, remember that trying to write this number down all the time, you'll drop a zero out or you'll add a zero or something funky will happen, and that's changing the magnitude by a significant amount. So we'll usually use 6.022 times 10 to the power of 23. So again, what that represents is 6.022, and the numbers after the decimal, there would be 23 zeros after the decimal if you move it. So this is called Avogadro's number. Not Avocado's number, Avogadro's number, because he's the one that really proposed this number to represent the number of particles in one particular thing. Oh, here we go. So 1 mole of any particle contains 6.022 times 10 to the power of 23 of that particle. So 1 mole of iron atoms, so again, saying 1 mole of iron atoms contains 6.022 times 10 to the power of 23 individual atoms of iron. 1 mole of water molecules contains 6.022 times 10 to the power of 23 individual molecules of water. So what it's saying here, this number is ginormous. It's pretty hard to imagine a number that's that big. The reason it's so big is because particles are so small. So to talk about a dozen particles, that's still so obscenely tiny that it's not even worth talking about a dozen particles or something. So it says, picture this, the Calgary Tower cost $3.5 million to build. If you had superpowers and could build 3 Calgary Towers every second, it would take you 2 billion years to spend 6.022 times 10 to the power of 23 dollars. So building 3 Calgary Towers every second, it would take you over 2 billion years. That's insane. Again, still not a good visual, but it's a really big number because again, particles and atoms are so very small. So it just takes a lot of them to be seen, much less work with them. I don't know why, you can look through the history of Avogadro, why this exact number is used, but that's where we called it, and that's kind of our the scientific community's decision on what 1 mole of a substance would be. So I'm trying to think what my next slide is. The mole and its mass. So if I had 1 dozen eggs and 1 dozen elephants. Oh, I forgot the word dozen. These have a different mass. And the same thing is actually true for compounds and elements as well. So, sorry, I just poked myself in the nose and it like made my eyes tear up. So how do we measure out 6.022 times 10 to the power of 23 particles of something? We use something called molar mass. And so this is going to come out of your periodic table, so hopefully you still have it close to you. So atomic molar mass is the average mass of 1 mole of a substance based on the percentage abundance of its isotopes. So remember, isotopes, they are differing numbers of neutrons. For a particular element. So different numbers of neutrons for elements. Again, just going back, this is back to chemistry A. Mass of an element, your atomic mass of something, is your number of protons plus the number of neutrons. Your number of electrons is negligible. It makes up basically nothing. So we know our number of protons for an element stay exactly the same. If you're talking about atomic number 6, that's carbon. It's always going to have 6 protons, but we can have different numbers of neutrons. So we can have carbon that has 6 protons, 6 neutrons. We can have carbon that has 6 protons, 7 neutrons, and we can have carbon that has 6 protons, 8 neutrons. So these are all isotopes of carbon. Where they get us, going off, is to these. So carbon 12 would be this one, right? 6 plus 6 is 12. Carbon 13 would be this one, and carbon 14 would be this one. So carbon 12 weighs 12 atomic mass units. So that's what AMU stands for. Carbon 13 weighs 13 atomic mass units. And carbon 14 weighs 14 atomic mass units. So in your periodic table, if you're looking at carbon, so again, atomic number 6, you see underneath the word carbon, it says 12.01. So you can see that that's the closest, pardon me, to carbon 12. But the reason that this 0.01 actually comes up is because there's a very little bit of carbon in the atmosphere on Earth that is actually carbon 13 and 14. So this is an overall average for all carbon. I don't have the number, and I can't make it up right in my head right now, of the relative abundance. So that's what it's saying, the percent abundance of isotopes, but probably 99.994% of carbon in the world is carbon-12, and then carbon-13 and carbon-14 make up that other little percentage, or fraction of a percent within the atmosphere. So that's where this 12.01 actually comes from. Hopefully that's clear what I'm talking about. If it doesn't make sense, let me know and I can try to explain it in a different way. Oh, I guess this sentence at the end is kind of saying what I was saying there. So it says carbon's atomic mass is 12.01 grams per mole. So we know grams is a measure of mass, right? And so saying grams per mole is saying grams in 1 mole of carbon. So that's saying 1 mole of carbon would weigh 12.01 grams. So that's saying 6.022 times 10 to the power of 23 particles, or you could say atoms, of carbon would have a mass of 12.01 grams. So again, this is 1 mole, 6.022 times 10 to the power of 23. So 1 mole of carbon would have a mass of 12.01 grams. So molar mass, again, this is what I was talking, or we had on that last page, that 12.01. So molar mass has the units grams per mole. It's used to refer to the mass of 1 mole of any pure substance. Your periodic table is organized to provide a practical way to convert the mole directly into grams. Knowing how many moles of a substance are in a specified number of grams of a substance is invaluable help. So it's saying the mass of 1 mole of an element, a molecular compound or an ionic compound, is called that substance's molar mass. So we'll see some of these calculations in the next little bit. So how is molar mass calculated? I already started this, but just to look again. So to explain this, you'll have to look at the key of your periodic table to find the atomic molar mass. So ours looks a little bit different. I think, oh, maybe I didn't post. Your notes actually probably look the same as this, but we know our periodic table looks a little bit different, but you can see how it converts. So if you look for lithium, so atomic number 3, I'm not sure what that 1.0 would be. Atomic number 3 has a atomic molar mass. So you see on our periodic table, it says 6.94 underneath the word lithium. And it does show our ion species and everything. So the atomic molar mass of an element is indicated within the box for each element. So again, your units are grams per mole for that. So what is the molar mass of each of the following? So you might want to quickly pause the video and give that a try. So looking at each of those, and note these little stars. This is like a free hint for you. There's 2 little stars here. So maybe pause the video and find the molar mass of each of these elements. So hopefully you used your periodic table if you paused the video there. So looking at gold, so periodic table, atomic number 79, we see that gold has an atomic mass of 196.97. And again, just like in physics where I said you need to write units, we should have units here. So our units of molar mass are grams per mole. We'll come back to the star ones in just a second. So W, that's tungsten. So tungsten used to be, I don't know if it was Latin, but it used to be called wolfram. That's why it's a W. So its atomic number is 74. So looking at the periodic table, it has an atomic mass of 183.84 grams per mole. Sodium, atomic number 11 is 22.99 grams per mole. Argon, so atomic number 18, one of our noble gases, is 39.95 grams per mole. And now back to these star ones. So bromine, so you can find bromine, it's atomic number 35, but remember that this bromine is found diatomically when it's on its own. So in its elemental form, it's found diatomically. So for bromine, we know it's 79.90 grams per mole, but we actually have two of them. So again, that subscript of 2 indicates that there are two of them. So our atomic mass for bromine is actually 159.80 grams per mole. And phosphorus, again, phosphorus atomic number 15 has an atomic mass of 30.97, but on its own, it's found polyatomically with P4, so that's 4 phosphoruses together. So times 4 gets us 123.88 grams per mole. So hopefully those ones make sense, figuring out the molar mass of each of the following. And again, what this is saying is if I had 1 mole of gold, so what that's saying is 1 mole of gold would have a mass equal to 196.97. 1 mole of tungsten would have a mass of 183.84. So just like I was saying before, 1 dozen elephants weighs more than 1 dozen eggs. So they have different masses, but again, 1 mole of a substance, 1 mole is equal to 6.022 times 10 to the power of 23 particles. So on to the next one here, it says determine the molar mass of a compound. No matter the formula is rather easy to determine. That sounds a little mean to write. It's not necessarily that easy. This is a complex idea and it's really hard to visualize, but as far as mathematics goes, it's not too complex once you get it. So it says to determine the molar mass of a compound, calculate the sum of the atomic masses of all of the atoms in that compound. So when we're talking about sum, we're talking about adding them together. Calculate the sum of the atomic molar masses of all atoms in the compound. So what is the molar mass of water? So it says in each mole of water, there would be 2 moles of hydrogen atoms and 1 mole of oxygen atoms. So the molar mass would be, so the way that we would calculate this, so 2 mole of hydrogen. So looking at hydrogen, finding it in your periodic table, so we're going to take 1.01, multiply it by 2. So that hydrogen will contribute 2.02 grams per mole. And then 1 mole of oxygen. We know that oxygen is 16.00. Again, there's only one of them. 16 grams per mole. So now if I add those up, we get 18.02 grams per mole. So that's the molar mass of water. So the next part says, what is the molar mass of ammonium phosphate? If I didn't give you this, you would be able to figure it out, right? Ammonium forms a 1+ phosphate PO4 forms a 3 minus. So we know in order to balance our charges, we need to have 3 of that positive charge to balance out the 3 negative charges. So that's where that chemical formula comes from. So if I ever just give you the name, you need to be able to write your chemical formula properly. Otherwise, you will not get to the right molar mass. If I had just put NH4PO4, we would end up with the wrong molar mass because we haven't created the correct compound. So none of that. So now looking, the molar mass for ammonium phosphate. So what that represents, so that NH4, we have it 3 times. And then we have PO4 as well. So in total, we have 3 nitrogens. We have 4, 8, 12 hydrogens. We have 1 phosphorus. And we have 4 oxygens. So that's all of the elements that are in this compound. So 3 nitrogens. We need to take 3 times our atomic mass of nitrogen, which is 14.01. We need to take 12 times the atomic mass of hydrogen, which is 1.01 phosphorus. So we're going to take 1 times the atomic mass for phosphorus, which was 30.97. And for oxygen, 4 times 16.00. So 3 times 14.01 is 42.03 grams per mole. 12 times 1.01 is 12.12 grams per mole. 1 times 30.97 is 30.97 grams per mole. And 4 times 16 is 64.00 grams per mole. So now what we would need to do is add up all of these, because again, nitrogen is contributing 42.03 grams per 1 mole of ammonium phosphate, and hydrogen is contributing 12.12 grams per mole of ammonium phosphate, and so on. So we want to add them all up. And so when you would punch those all into your calculator, you would get 149.12 grams per mole as your molar mass of ammonium phosphate. So find the molar mass of carbon dioxide. So you need to be able to write your chemical formula for carbon dioxide, CO2. So we have 1 carbon, we have 2 oxygens. Sorry, I'm going to run out of room. I didn't leave myself enough here. So 1 times 12.01 is still 12.01. 2 times 16 is 32. So when I would add these together, 44.01 grams per mole. So the molar mass of carbon dioxide is 44.01 grams per mole. So you can see it's a little bit of a process, and hopefully you can see your ability to write chemical formulas properly still is very important. Oh, I forgot there was one in here that I didn't really like. Okay, so for this one, we'll do a little bit of practice. It says calculate the molar mass of each of the following. So remember, you need the correct chemical formula. If you get the chemical formula wrong, your molar mass will be wrong. There's no way to get it right if you've got the formula wrong. So show your work on a separate sheet of paper, whatever, I don't care. So what I want you to do, once I'm done talking here, is pause it and do the chemical formula for all of these. This one's a little bit confusing. Maybe we'll just, actually, let's just leave this line out. Don't see any other ones that are funky. Sodium, sodium bicarbonate is sodium hydrogen carbonate. So just if you get stuck there. So again, pause it and write out the chemical formulas. Then I will write all of mine down, double check it, and then we'll pause the video again and you'll calculate the molar mass and make sure that you can get it right. So pause the video now and write out your chemical formulas for all of these. All right, so hopefully you have done that. I'm going to write out the correct chemical formula. If you got anything wrong, please go back and look as to why you got it wrong, because the skill hasn't disappeared of writing chemical formula properly. So calcium hydroxide, gold 3 chromate. That's a 2, sorry, I can't really write small enough. This is a 3. Mercury 2 oxide. Uranium 4 fluoride. UF4. Ethanol is one of your memorized ones, so C2H5OH. Manganese 4 bromide is MnBr4. Aluminum sulfide, Al2S3. Potassium permanganate is KMNO4. Sorry, that looks weird. Carbon disulfide, CS2. Sodium hydrogen carbonate or bicarbonate is NaHCO3. Phosphorus trifluoride is PF3. Zinc oxalate. Is oxalate on your chart? Yes, it is. Good. Is ZnOCC. Oops, 2 O's. OOCCOO. Sucrose is C12. Again, another one of your memorized H22O11. And barium sulfate is BaSO4. So hopefully you got all of those right. If you don't, you need to look back to Chem A. If you're making the same mistakes with these, your multivalent, if you're messing up tries and dies and stuff like that, or if you're not putting brackets in the right spots or anything like that, you need to go back and figure that out. So your next step is figure out the molar mass. There is not nearly enough room in this little box to write out everything, so you might need to do it on a separate sheet of paper. But I'll do that first one together again just for one piece of practice, and then I want you to pause it and do it all. But calcium hydroxide, which we wrote the chemical formula as CaOH2. Oh, let's put the bracket in the right spot, Tanya. CaOH2. So what that represents is 1 calcium and 2 of those hydroxide. So 1 calcium, 2 oxygen, 2 hydrogen. So calcium is 40.08. Oxygen is 16.00. Hydrogen is 1.01. So if I added that all together, I would get 74.10. I'm going to put it, you don't have to, grams per mole. So your answer for the first one for the molar mass of calcium hydroxide is 74.1 grams per mole. So I want you to pause the video now and calculate out the molar mass of all of those guys. So it'll take you a little bit of time and probably a sheet of paper, but pause it, do those, and then look over with my key. So I'm not going to do absolutely every one of these. I'm going to write out what I have. Make sure your answer matches up. If I'm off by like a 10th or 100th, just double check how you put it in. Maybe we have something funky, but if you're way off, you've obviously done something incorrect. So the molar mass for gold 3 chromate, I'm going to get lazy and stop writing my units. They're up here anyways, so I'll just write the numbers associated with it. Sorry, I'm trying to delete that line out of my mind. Potassium permanganate is 158.04. Carbon disulfide, 84.01. Sodium hydrogen carbonate. Uh-oh. I wrote it in the wrong line. Probably messed you guys up. Sorry. 76.15. 84.01. Phosphorus trifluoride, 87.97. 153.43. Sucrose, which was probably a bit of a process to calculate, is 342.34. 233.40, I believe, and 114.26. I can see I have whiteout on a couple of these, so I obviously made a mistake before. Hopefully I don't have any of those wrong still. But have a peek through. So now you have your next worksheet, and it's kind of the same idea as we just had there, calculating the molar mass of all of these. So now that you've done the practice and you know what you're doing, you can figure out the formulas and molar mass. Oh man. Oh man. I'm a doofus. This is exactly what's in your notes package. You know what? Let's not do sheet CB7 because most of these are the same as your yeah, they all are. So the benefit of you having listened to the notes is now you don't have to do the worksheet. So there you go. Go enjoy your day. Do CB8 next. Okay, see ya.